We've done some electron dot structures, we've done some Lewis structures, simple Lewis structures. We've talked about the octet rule, we've talked about throwing the atom with the lowest electronegativity, or maybe the one with the most potential bonding locations in the center, and now we need to practice. This is a skill more than many others where practice makes perfect, and it allows you to bump your head against some situations you may not expect, and it allows you to plan for contingencies. Muscle memory, that's what we're really going for here. So I'm going to be drawing a lot of pictures, and I don't want to be wasting my big paper, so I have the small paper here, and the first thing I want to look at is Lewis structures for ions. All right, and as a quick reminder, and we've used these vocabulary terms plenty at this point, but we have cations, right? And those are positive, and they are positive because they have lost electrons. We're not changing the number of protons because that would change the identity of the atom. That would be a nuclear change. When we're getting charges, we're changing the number of electrons. We also have anions. Those are negative, right? How do you get a negative charge? By gaining something that's negative, and those are our electrons. And that is the basis for these Lewis structures, is if you have a cation, you're going to remove electrons, and if you have an anion, you're going to gain electrons. So we will put that in simpler terms. I'm laughing. Lost electrons, right? Remove dot. And add dots. All right? And I know that sounds dumb, but again, I want to highlight the idea that you don't really have to know much to be able to draw these structures. It's a puzzle. You're connecting dots using information you get from here. Okay? So we'll start with something that is fairly straightforward. It's a compound closely related to water that we've seen before many times, and that is the hydroxide polyatomic ion, OH minus. Like if we have a goal here, we're drawing some Lewis structures, all right? So this is exactly how I would set this up. We said what we're going to do, lower electronegativity goes in the center except hydrogen. Well, that means oxygen goes in the center. Oxygen, group 16, 6 valence electrons, 6 dots, right? So we've got our oxygen, 1, 2, 3, 4, 5, 6. All right, I see 2 potential bonding locations. I need to attach one thing. In this case, it is that hydrogen. Hydrogen is in group 1, so that's 1 valence electron, 1 dot. And you may recall me just saying, all right, hydrogen dot, there's our bond, right? At this point in time, hydrogen, that line counts as 2 electrons. Hydrogen's needs for the octet rule are met. Oxygen, 1, 2, 3, 4, this counts as 2, 5, 6, 7. That's not 8, as you may recall. There is a catch, though, right? And that catch is right here, right? That's an anion, so we're going to add equal to its charge. And a minus implies 1 minus. So something I tend to do is I'll either make the dot much larger, or I'll make the dot a different color. That's not a legit necessarily way to do it, but it's good visually for me to say, hey, that dot came from somewhere else, all right? And then part of these drawing these ionic structures is you put them in brackets with the charge outside. All right, so that is the hydroxide polyatomic ion, and you can kind of think back to water. If I didn't have this charge, but I had another H, then I would just have that hydrogen down on the bottom, and we'd have H2O, right? So adding an H plus is what gets us there. Similarly, I want us to compare a compound we drew out previously, in fact, a couple of them. And the first one we're going to look at is oxygen, which we drew as a diatomic, and I'm just going to quickly skim through that one. O2, oxygen, group 16, 6 dots, 1, 2, 3, 4, 5, 6. Another oxygen, group 16, 6 dots, 1, 2, 3, 4, 5, 6. Our reasoning, first of all, connect those dots. 2, 4, 6, 7 is not 8. 2, 4, 6, 7 is not 8. So I'm going to take these other potential bonding locations and make another bond. So that is our diatomic oxygen. And I want us to compare that to peroxide, the peroxide polyatomic ion. Because they're very different things. Obviously, the charge is the difference. And let's give that a try as we're drawing this picture. Oxygen still from the periodic table has 6 valence electrons, group 16. Oxygen from the periodic table still has 6 valence electrons, group 16. We connect that dot. At this point in time, each oxygen has 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And that's not 8. We don't connect these 2 potential bonding locations, though, because we've got to add some electrons right there, and so I'll highlight that. We need to add, in fact, 2 electrons to this. So I'm going to put in my extra electron, and put in my extra electron, and then put it in brackets and put the charge outside as a 2-. So when you look at diatomic oxygen neutral, has to double bond to get both oxygens to have an octet. When you look at the peroxide polyatomic ion, it has 2 extra electrons, only a single bond is needed. All right. Similarly, we're going to take a look at ammonia versus the ammonium polyatomic ion. So Ammonia Nh3, which I think we might have looked at in a previous video. Nitrogen, we check our periodic table, nitrogen, group 15, 5 dots. And we already know hydrogen, 1 dot, 1 valence electron. So I'm going to draw my nitrogen. If you look at the electronegativities, nitrogen's a 3.0 and hydrogen's a 2.1, but hydrogen doesn't go in the middle. That was a specific rule, actually. Hydrogen won't go in the middle. It only has 1 bonding location. So nitrogen, 1, 2, 3, 4, 5. And we need to attach 3 things. One of them is going to be the hydrogen, and it brings a dot, and the hydrogen, and it brings a dot, and the hydrogen, and it brings a dot. So we have NH3. Now let's compare that to the ammonium polyatomic ion. All right, same deal as before. Nitrogen is in group 15. It has 1, 2, 3, 4, 5 valence electrons. We need to attach some hydrogens. Hydrogen, oh look, it's 4 instead of 3 this time, right, for the polyatomic ion. So I'm going to attach it, I'm going to attach it, I'm going to attach it. And listen to these words very closely, because this is going to be a theme as things go. Do you see what we would predict as a potential bonding location here? No. Do we need to attach something else? Yes. Then do it. All right, you see how that works? I got to add another hydrogen. Well, we have to. Just do it. All right, and you'll get, again, that's why we practice, is things like that come up. Now, as you look at it, nitrogen currently has 2, 4, 6, 8, 9. And that's more than 8, in case you were keeping track. We can handle it, though, because of what is right here. We're going to remove dots if there is a positive charge. And so right here, this dot right here doesn't exist. It has been removed. And a lot of people are like, oh, where did they go? Well, for instance, this dot may have gone to a peroxide, right? So that it can get those extra 2 dots. The things that are losing electrons are giving them to things that are gaining electrons, all right? So that dot is no longer there. We put it in brackets and we put our charge on there, the ammonium polyatomic ion. I'd like to keep running through some other polyatomic ion examples, and I tried to rearrange this in such a way that our important information is still visible. And let's try another polyatomic ion. We haven't defined that except in our nomenclature videos. Polyatomic ion is a covalently bonded group of atoms with a net charge. So things like sulfate, phosphate, carbonate, right? Ammonium, cyanide, thiosulfate. Those are all polyatomic ions. And we looked at a couple right there. Well, 3, hydroxide, peroxide, and ammonium. And I want to look at some other ones just so you can kind of get a feel for how this happens and how it relates to the other ones we've seen. The first one I want to look at is the hypochlorite ion, OCl- or ClO-, depending on which way you're looking at it. We follow our rules, which were find them on the periodic table. There's oxygen and chlorine, 6 dots, 7 dots, all right? And I'm not really worried about what has the higher electronegativity because there's only 2 things. There's nothing to put in the middle, right? So first up, I'm going to draw the oxygen, which has 6 dots. 1, 2, 3, 4, 5, and 6. I see 2 potential bonding locations. I need to attach one thing, that is the chlorine, which has 7 electrons. And it doesn't matter where you put it, remember that. I'm just going to try and make sure that my single dots are facing. So here's my Cl. It has 1, 2, 3, 4, 5, 6, and the 7th one's going to make a bond right there. At this point in time, chlorine has 2, 4, 6, 8. That's good. Oxygen, though, 2, 4, 6, 7. That's not enough. And we have to take into consideration this important thing, which is we had a charge right there, and now we can add that extra electron as part of that charge. And now oxygen has that octet. We do still need to put it in brackets and put a charge on the outside. Just putting a minus or a 1- is fine. A few other ones that it would be worth glancing at. The Cyanide Polyatomic Ion, Cn-. We've got carbon and nitrogen. Carbon, group 14, that's going to be 4 valence electrons, 4 dots. In nitrogen, group 15, 5 dots. And there's only 2 of them, so it doesn't really matter what's in the, quote, middle. There is no middle. So carbon, 1, 2, 3, 4, because it's in group 14. Nitrogen, 1, 2, 3, 4, 5, because it's in group 15. So at this point, this isn't something super obvious like this. This is a situation where I have 3 potential bonding locations and 2 potential bonding locations. And I think if you look back in your memory to the video we did with like diatomic oxygen and diatomic nitrogen, we've got a plan. I don't have any other atoms to attach, so I'm just going to have to continue attaching these atoms to each other. All right, and that's our strategy. Our system is very straightforward. I have a single dot and a single dot. Let's make those into a bond. All right. At that point in time, we have 2, 4, 6, 7, close. 2, 4, 5, 6, not as close. But we still have some potential bonding to take place, so let's do it. It should not bother you in any way that this electron in our drawing is over there, and this electron in our drawing is over there. If you think back to what I was trying to bludgeon into your head in the previous examples, the orientation, how things are arranged, doesn't matter for Lewis structures. What does matter is how many single dots and how many double dots or lines you have, all right, pairs. So I'm going to take this and this, and we can move them wherever we need to. So we end up with C triple bond N. That gives the nitrogen 2, 4, 6, 8 valence electrons. Carbon still only has 7, and I think you can predict that we need to make use of that negative right there in solving our problem. This needs 1 extra electron. There it is. And we put our 1-. And again, in the big picture, you wouldn't show those crossed out electrons. That's not part of the drawing. The actual Lewis structure would be something like, all right. But I think, again, in your notes and in seeing the process, it's really useful to cross out those electrons and show that they were there and that they went somewhere else. I want to continue on with this theme of polyatomic ion examples that are getting slightly more complicated. And we're going to give the carbonate polyatomic ion a try right here. So carbonate, CO3, 2-. So you've heard of it. Baking soda is sodium bicarbonate, sodium hydrogen carbonate. Limestone is calcium carbonate. Washing soda is sodium carbonate. So carbonates are pretty popular. We're going to look at our things here. All right, I've got 4 things. That's way more than the 2 I've been dealing with. If you look here, carbon, group 14, that's going to be 4 dots. Oxygen, group 16, 6 dots. And in terms of electronegativity, carbon's a 2.5, oxygen's a 3.5. Lower electronegativity, weaker in that tug of war, that's the one that's going to be in the center. That's the one that's going to be able to do more bonding energetically. So I'll draw my carbon. 1, 2, 3, 4. I need to attach 3 things. And again, this is my strategy. This is exactly how I do them. It's not just me talking. I'm going to take my oxygen, group 16, 1, 2, 3, 4, 5, and bond, right? Oxygen, 1, 2, 3, 4, 5, and bond. Oxygen, 1, 2, 3, 4, 5, and bond. All right? And now I'm going to see where I'm at. Each of these things has 1 potential bonding location. Right here we've got 2, 4, 6, 7, 2, 4, 6, 7, 2, 4, 6, 7, 2, 4, 6, 7. I'm not going to worry about the charge until the end. All right, and maybe that is something slightly different. There's all kinds of ways to do Lewis structures, but I want to bond what I can and then worry about everything else later. And if you look here, there is a potential bonding location there and a potential bonding location there, or there and there, or there and there. And that fact that we have options we'll take care of later in our resonance structures. But for right now, I'm just going to pick one. I'm just going to say, all right, that one and that one are going to make a bond for us. Now, if you look, oxygen 2, 4, 6, 8, but oxygen 2, 4, 6, 7. Ooh, carbon 2, 4, 6, 8, 2, 4, 6, 7. So this oxygen is missing an electron. This oxygen is, oh, look, hey, right there. 2- means we can add 2 electrons. It is not a coincidence that we need 2 electrons And again, those crossed out things wouldn't be on there in your real answer, but I think it's useful, again, in your notes. Also, the double bond could have been here or here, and as I said, we're going to deal with that later. In fact, you could have drawn this some super mess, like carbon, oxygen, 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 dot, 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 dot. All right, that would be totally okay, although it makes people very uncomfortable. All we're worried about is the number of dots and the number of things that are attached. All right, one last one that I want to sneak in for our ions here, just so you can get a feel for what if things look scarier. All right, and I think a classic example of one that looks scarier is the acetate polyatomic ion. If you've ever had salad dressing or anything like that that has vinegar in it, when we talk about vinegar, it is dilute acetic acid, which is just the acetate polyatomic ion with an H on it. So the acetate polyatomic ion you may see written as C2H3O2-, and that's true. But when it comes to organic compounds like that, very often you're going to see them written in a way that gives you an idea of what the structure is going to look like. So I will almost never write acetate C2H3O2-. In fact, I'll write it CH3COO-. And then many years ago, one of my students said that was Chiku, so that's what I always say for the acetate polyatomic ion. Chiku, Chiku. So why is this useful to us? Because this actually tells us what it's going to look like. And it seems really, really scary because there's so much stuff there, right? We've got 7 things as opposed to like 3 or even 2 things. But we can handle it because it tells us exactly what things are going to look like, all right? So it's saying that I have a carbon, 1, 2, 3, 4. And I'm going to attach 3 hydrogens. Hydrogen, hydrogen, hydrogen. And it doesn't matter which side those hydrogens go on, but we do take note that we're going to have to attach another carbon, which had 4 dots, right? And now I need to attach 2 oxygens to that carbon. And so I'm going to attach an oxygen, dot, 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 right? And another oxygen, dot, 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 dot. So I've used up all of those pieces. Are there any other bonds we can form? Well, this carbon's good, 2, 4, 6, 8. Hydrogens are good with 2 each. This carbon, 2, 4, 6, 7. That's not enough. Oxygen, 2, 4, 6, 7. Oxygen, 2, 4, 6, 7, right? So we can make use of these other available potential bonding locations. If I draw that in, I've got a double bonded oxygen. That solves the problem for oxygen and the problem for carbon. But we still only have 7 up here. Oh yeah, right? We had a charge, and that's telling us we can put that extra electron in wherever we need it. So again, you will see me most often save the charges for last to do any bonding I can before then. But these structures, especially when they're octet-based, it's all the same thing. And you just practice, practice, practice. You can put the electrons wherever you need to. There's consequences, and we'll get into ways to assess that. But that's all there is to it. Find it on the periodic table, write some dots, connect the dots, and then add or subtract dots for ions.